Okay, morning everybody. Today we are not going to take on some new theory, but we are going to do some examples. We are going to see some examples on opcode conversion from the assembly language, so that whatever little doubts you had in the last class, that will be cleared, absolutely clear this time. Okay. So this is the instruction format which I introduced to you last time. I said they could be 4 bytes or they could be 6 bytes also. So only 4 is shown here: low dispersion, low displacement and high displacement. They could be another 5 and 6 bits also. So this is the general format of an opcode, right? Machine language. From the assembly language. So this also is another format. For certain instructions you can just write only in 3 bits. Okay, this is the opcode. Like for, we'll see the examples. Like for move direct syntax, so you don't require this big N opcode. Within a small opcode of 3 byte, we can finish off with the machine language. So these are the two standard formats which are generally used for converting an assembly language into a machine language, right? So we'll take on some examples. So the first example which we are going to take out here, we'll discuss out here, is move AX BX, right? So this is the format. So first we need to refer to the manual, right? In the manual for the move, what is the opcode, right? You don't have to remember anything. These are the 3 things which will be given to you. This is the manual, right? So from the manual, from these 3 charts you can use from the manual, and frame and instruction, frame and machine code, or an opcode, right? So you just need to know where to refer what. Okay. So if you see under the move, there are various. I have just taken a snapshot of only 2 instructions. There are for each of the move there is a different opcode there. So in this case it is register to register. So we need to see under the move I have just taken 2. There are many of them. Okay, register to register is 1 triple zero 1 0. So I write 1 triple zero 1 0 out here, right? And now the direction, then comes the direction, right? So here in this case, since it's a register to register, you can put anywhere. Here also you can put the source register, and here also, or source and destination can be interchanged. Accordingly, D, you need to set your the value of the D. So let's take an first example where I am going to set D is equal to 0. Then it is going to move from register to RM, right? So that is going. Now it is, since it is AX and BX, that means we are going to handle a word and not a byte. So a word is been set as 1, and then mod is 1 1, because it is a register mode with no displacement. Okay, so mod becomes 1 1. And then you have a register. Here we are moving from we have put D is equal to 0, that is, it is going to move from register to register stroke memory. So from, this is the source, so this is going to be BX, okay, not AX, because this is the destination, this is the source. So you need to see what is the thing for BX. BX is 0 1 1. So we put 0 1 1 out here. And what is the thing for A? The code for A register is 0 0 0. So you put 0 0 0 here. So it is pretty simple. So in case you get these things in exams, you should be able to score 100% in these kind of problems. Okay, and then you write the necessary hexadecimal number from here, right? So this is the hexadecimal number for this. So this, you know, from binary to hexadecimal, how to convert and write these numbers. Okay, these 4 bits, this stands for 8, and from here to here 1101 stands for D, 1009 1 stands for 9, and again last, the most significant, 1000 stands for 8. Okay, so the other method of writing the same thing here is by putting D equal to 1. So the only change which would happen is these will get interchanged. Okay, 0 0 0 0 and 0 0 0 1. Is this thing clear to all of you? Is it clear? Is there any doubts? Anybody?
So could you explain it one more time, sir?
Yeah, okay, sure, no problem. So this is the format for an opcode. Okay, so the first byte is for the first 6 bits is the opcode for the instruction which is given here. Okay, like whether it is move or with whether it is add, subtract, and also we need to refer to the chart which is given by the manufacturer. Okay, by the OEM. Okay, the instruction for code. So when it's a PDF document, I'll share it with you, or it's there in the textbook also, right? So we need to refer to that. Okay, it is given by the 8086 manufacturer, by the Intel. Now for move, within move also, this is the heading, and there are several move types of move. So we need to see what is the move here we are which we want here. It is AXAX, that means move register to register. So this is register to register, from register memory to register, and this is the opcode 1000010. So we put 1000010 here, right? And then the next bit is D. D means the direction of flow. Okay, this is the source register on no, these are the two registers. So here if we write 0, then the data will flow from register to memory, or if you write D equal to 1, the data will flow from register to memory to register. Okay, in this case it is both registers. So here also we are going to put a register, here also we are going to put an register. So we can use either D0 or 1. So suppose we take 0 here, then this will become source, this will become destination. Okay, so that is why we have taken 0 here. Since we are handling AX and BX, which is a word, we put 1 here. Now mod is here 1 1. This is again available in the chart, that it is register mode. 1 1 indicates it's a register mode because we are handling only registers here, so it is 1 1. And now this is the source register. The code for the BX, okay, is 0 1. For BX is 0 1 1. So we write 0 1 1 here, and the code for AX is 0 0 0. So we write 0 0 0 here, right? So if we change the direction here to 1, right, then these source and destination registers will get interchanged. Is it clear now?
So here, no displacement means that we are just moving values and there won't be any overflow when the operation happens. Is that right?
No, no. We'll see what displacement means. If you write, say, within a square bracket bx plus 50, right? So that is offset, an extra offset when we give. So that is known as the displacement. Okay. We'll see one example, it will be clear. Okay, so this instruction gets over within 2 bytes, right? So this is not used. Okay, we'll what is a displacement will be clear in the next example also.
Excuse me, sir.
Yeah, tell me.
So when we give this instruction move AX comma BX,
Yeah.
What hex code would actually be passed on to the processor? Would it be anything random between 8 9 D8 or like 8BC3? Would they have equal probability or one is preferred over the other?
Actually, the compiler, what we do is we write the code in assembly language and we give it to the compiler. So the compiler compiles it and it generates an opcode which is fed into the microprocessor. Okay, it depends on the compiler, okay, on what kind of compiler we are using. Okay, so I'm not very sure, but it doesn't matter really, what it does. Okay, it might be I cannot be say for sure that it will take D equal to 0 or 1, but it might have its own algorithm to convert the assembly language we write into the machine language, right? When if we are doing it manually, then we can use either of them, it doesn't matter. Finally it will be executed in the same manner. The final results will be the same, so it doesn't matter.
Understood, sir.
Okay, so let us take one more, immediate addressing. Okay, here it is move CX, okay, AD4C. That means we want to put this particular data AD4C into the CX register. So this is the command which we need to write. Okay, now if I see under the move, so I have taken a snapshot. Now I have taken even the third line. If you see the third line, immediate to register, okay, it means immediate to register. For that, the opcode is 1011 W, which is whether it is a word, and then the register. Okay, it's an so it's not a 2 byte register. This thing is in a single byte opcode. Okay, move immediate one. Here if you see, it has got more number of, so accordingly we write this. So here we are going to write now 1011, and then whether it is an single byte or it's a word. It's a word here. See, if it because we are going to move it into the CX, so we write W, and then it is a register, right? Into what register we need, right? Into the what register it is, we want to move it into CX, right? So let me okay, so CX stands for 010, right? Word is equal to 1. CX stands for 001, so I put 0001 here, right? And then what is the data which requires to be put there? Okay, that is 4C and AD, right? AD 4C. So in the lower displacement we are going to write 4C, and in the higher we are going to write AD, right? So this will become the entire, this will be the entire code. In the 1011 stands for B, and then is yeah, and then this stands 1011 stands for 9, and then 4C, and then AD. Okay, so is the purpose of lower dispersion and higher dispersion clear? So in this case we require lower displacement and higher displacement. We require these bytes also. So this will be the opcode. It is a 3 byte instruction. This one is a 3 byte instruction now. Is it clear? How? Yeah, Ruben has got a doubt. Sir, isn't register supposed to be in byte 2? No, Raji, if you see, there are two different. Let me go back. This is also an valid format. Okay, for certain instructions, for immediate kind instructions, within byte 1 the register is available here. Okay, and Ruben, not for immediate to register. Yeah. Okay, so this is also a valid format. This is also sir, which instructions are 3 byte? No, any the instructions can be from the opcodes will be from 2 byte to 6 byte. It could be anything. So you need to refer to the chart depending on the instruction, and then we can't be sure. Like in the, we'll see, like now the first example which we saw, it was only 2 byte, right? Now we have seen a second example where it is 3 byte. So now we'll see other examples where it could be 4 byte, 5 byte, 6 byte also. So it depends on the instructions. No, Abhinav, is it okay?
So can we say whenever we are moving values from register to register, or register to memory,
Okay.
or memory to register, it will be 2 bytes? Can we say that always?
No, we can't say that always. Okay. If there is an offset and all, we'll see. Each example by example we need to see. Okay, when we do some examples we will see. Okay, yeah, others, the thing is we have written this code, right? Byte 1 and byte 2 is like move AD4C, so we need to also give this data also to the opcode, right? What is the data which requires to be fed to CX register? Okay, the first byte only says opcode, it says only move. Okay, then it says it's a word, then it says register, which register the data needs to be moved. Okay, so the first byte only indicates it's a move instruction. Okay, it's a word and it's a register. Now it says move immediate. Okay, this opcode stands for move immediate. Then it says a word, and it says into CX register. Now what is the data which requires to be fed? That also we need to give. So we give lower display. No, there are two more bytes we are going to use. This is known as low displacement and high displacement. Okay, this displacement nomenclature has come from actually the offset which we give for the memory, but here it is not actually displacement, it's the actual data which we are feeding in these two locations. Okay, now 4C. So you just have to remember that the first, it will always be the LSB digits, and then it will be the MSB. So it is not AD and 4C. You have to be careful with this. It is always going to be 4C and then AD. Okay. So this is known as Little Endian system. When we see the hardware, I will explain you now why we have in 8086 now the lower bit is placed here and why higher. This will be absolutely clear when we see the hardware implementation. Okay, so what's the advantage of placing the lower bit here and higher bit here? Okay, is it clear, Adarsh?
Excuse me, sir.
Yeah, tell me.
So here we didn't need the D bit because one of the operands is memory. I mean, like it's immediate, so it's not a register. So D bit has no significance. But how did we do away with the mod bit, sir? Like the mod section, those 3 bits there.
If you see, mod is not really required here. So once the microprocessor reads the first 4 opcode data, okay, once it reads the first 4 opcode data, it will realize that it is an a move immediate command which is there. Okay, it will decode this. Then it doesn't require the mod data, because it is very clear now. Once you read, okay, what we need to do is we need to tell it the even the direction is not required, because it is an immediate. So those things have become redundant. So only word is required, and what is the register, and the data is required. So if you see, these 4 will be unique, and it will not be there in any other instructions. So the moment the microprocessor reads these first 4 bits, it will realize what is the next which is going to come. So accordingly, it will get decoded, and those data become redundant actually. Is it okay?
Yes, sir. So the mod bits are required only when we are moving like register to register, where the opcodes might be redundant. So we'll have to make a decision based on the mod bits.
Yeah, correct. So the entire, because the decision making has to be different there. So depending on the mod, it will be different. Okay.
Understood, sir.
Okay. Ruben, endedness. I have a slide on that. We'll discuss that. Aditya, because if you see 1011, if you see move instructions here, right? So the moment, if you see if he reads only this 1011, right, it is unique. This 1011 is not there in the the other format. If you see, it is 1000 and other bits are there. So this 1011 is unique for a smaller type of a move immediate type of instructions. So the moment it encounters 1011, the computer would realize that this is what is going to come ahead of this is going to be a shorter format. Is it clear, Aditya? Okay, so you won't have a register memory 2 from register with 1011 and something. It is totally different here. So when it starts reading 1011, it will automatically understand, okay, the rest of the things is related to an immediate addressing mode. So accordingly, it will take in shorter instruction format. Okay. So let's take one more example. Okay, Little Endian. Okay, it is there is nothing.
I have a small doubt. Could you go to the previous slide?
Yeah, tell me.
We have two different codes for two different operations, where one is immediate to register slash memory, other one is immediate to register.
Yeah,
Why
on
should
top
we
of,
have,
yeah, yeah.
if both operations can move immediate to register, why do we have different codes?
No, no. If it is immediate to memory, we need to use the of this code itself. Okay. When we are moving, doing it with immediate to register, we could use either of them, but this is more efficient. This is going to be a smaller one. If you try to compile with this also, we can do that. Okay.
So,
Immediate to register also.
but both do the same thing. So why is it they have different codes?
No, when we say immediate to register stroke memory, in that case, when we are dealing with memory, so we need to specify more things. Okay, there is an example on that. If you are going to put some immediate data into a memory location, then we will require the mod data also. We will need to give the displacement and things like that. It will be clear from an example. Okay. Uh,
So,
yeah.
why are we considering AD4C as displacement?
Uh, yeah. Actually, the name of these registers have been placed as displacement, because generally we'll see in some examples. Generally, these bytes are used in when I go back here. In this format, these registers, generally we use these registers for giving the offset displacement. Okay. And here, because it has been the nomenclature has been given like that, so we are calling it as displacement, but otherwise this is actually carrying the data which we are going to move into the registers. Okay. So don't pay too much attention into the nomenclature of these registers. Okay. Why the nomenclature is, probably in one more examples we'll see where it is used as a displacement. We will see that. Okay. Okay. Little Indian and between Big Endian, only the difference is, you see, the in 8086, remember always when we talk about an a word, it always will be fed in an odd even memory first, and then an odd memory. So the pair will be made even and odd. Okay, starting from even and then ends at odd. Okay, the memory locations, and then you have the lower bit coming into the if you see here. Okay, in the low, this is the lower bit and this is the higher bit. Okay, so the way it is written here, and here it is in the big, it is in the odd register, in the even register, and a higher displacement is written, and here it is written at 27, here it is written the other way around. Okay, so don't worry about this thing time being, because when we see the hardware implementation, we will see that in 8086 we are going to use Little Endian. It has got some advantage in doing so. Okay, so it is a purely hardware requirement, nothing to do with software issues, or it's nothing to do with number systems and all. It is just that it is very easy to because 8086 uses 8 bit of, it can store, if you have to store only 27, it will use only 1 byte of memory space. Okay, it is not that all the 16 memory space will be blocked. Okay, so although it is an 16-bit memory cell, it is divided into two sets of 8-bit memory cells, odd and even bank we call it. And when we have to store 8-bit data, it will store as single bytes, and when we have to store two like a word, it will take 2 bits. It is not that every time, even if you have to store a byte, it will consume the entire 16-bit memory space. It's not so. So in the hardware implementation, so if we do if we use the little Endian, it will solve our lot of issues. So this I will discuss in detail when we discuss about the hardware implementation of memory organization, maybe next week. So that portion is to little later. So during that these things will be clear. Time being, you just remember the format in which the data is written here. Okay, so let's take one more example here. Now here we are moving AX to move AX, right? That what is this within square bracket when I write? It is not that we are going to move 1 2 3 4 into AX. What we are going to move is, we are going to move the 1 2 3 4 represents a memory location, and whatever is the data available in that memory location, that needs to be moved to AX. Okay, so now if you see the opcode, now 100 no, 010 is the opcode for a move instruction. Here D has to be 1 here, right? Because there is only one register here, right? So now this is not a register anymore. Okay, so there is only one register here, which is AX. So now this is so D has to be 1. So here we are going to put A. So A stands for 000. So I have put 000 here. AX. So W is 1. Now if you see the mod, okay. Now if you see the mod here, if there is one. 1 2 3 4 is now the displacement. Why do we call this as a displacement? Okay, this is an what does 1 2 3 4 means? The DS segment plus 1 2 3 4 is the displacement. Okay, we have seen that how the physical address is generated. So 1 2 3 4 is the displacement from the starting point of the DS segment, right? So that is why we call this as 1 2 3 4 as a displacement. So now if you see here, okay, 1 2 3 4 is an 16-bit displacement. So mod is 00, displacement when RM is equal to 110, 16-bit displacement. So we put the mod as 00, and if you see 110 here, 110 is displacement 16, right? 16-bit displacement. So we put 110 here, and now low displacement and high displacement. So here low displacement is 34, high is 12. So that is how this name of these registers have come as low displacement and high displacement. But in some instructions, instead of displacement, we give the data also. Okay, but nevertheless the name has been given as low displacement and high displacement. So is this thing clear to all of you? Is there any doubt?
So can you just please explain the last part again for the memory one?
Okay.
The displacement.
Okay. See, this is the displacement from the what does this 1 2 3 4 means? It's a memory location address, right? What is the address? 1 2 3 4 indicates like data segment, whatever is there in the data segment, plus 1 2 3 4, right? How do you calculate the physical address? Data segment into 10 plus 1 2 3 4, right? We did that physical address in the tutorial also. So 1 2 3 4 is the displacement. So so automatically the physical address will be calculated DS into 10 plus 1 2 3 4. Now we need to specify the, so that's why this 1 2 3 4 is the displacement. Okay, so that is why we use 1 2 3 4. So this 1 2 3 4 is known as the displacement. So we write here 3 4 and 1 2, right? Yeah, 1 0. Yeah, memory mode with 16-bit displacement. No, that is slightly different. What it is memory mode? What is a memory mode with 16-bit and memory mode? Here, yeah, 1 0 also could be used, but here specifically it is given for memory mode with 16-bit displacement. So we need to use this 0 0. Okay, we will see this also, a example of this also. Okay.
Sir, so if our register memory is not 110, then we use mod equals 10.
Yeah, yeah, correct. If R
And we,
is not 110, then we need to use 10.
and our RM is 110 because we are doing a displacement.
Oh yeah, we are doing a displacement of 16.
Yes, sir.
Okay, so we take one more example. So now move bx. Okay, now here we are going to move the contents of cl into memory location. And what is the memory location? The offset of the memory location is given in bx register. Okay, so this is just a small program which is written here. Okay, in which what we are trying to do is okay, in the physical address, now what we are going to do is we want to store value 0 1 2 3 4 in these registers. Okay, in these registers. So we are writing a program which will push value 0 here, value 1 here, value 2 here, value 3 here, value 4 here. Okay, these are the numerical values which we want to push into these registers. So how do we write a program for that? Okay, so this is a small example of a program where we have initially put al is equal to 0, cl is equal to 4. Okay, cl is equal to 4 means 1 2 3 4 5. So this is a counter, so 5 values, so we are putting into cl is equal to 4, right? So 0 to 4. So these are this is just a counter to initialize a counter so that it stops after 5, because we are interested only putting 5 values. Okay, and initially bx is 0. So we are going to bx is the bx is equal to 0 means this is, it is going to generate an physical address when we write move bx. So this is the physical address. Okay, so if ds is equal to 0 1 0 0 for an example, plus one more 0 bx, here it's 0, so it will generate 0 1 0 0 0. That will be the physical address. In that 0 will be moved. Okay, then you increase al, because in the next memory location I want 1 to be stored. So I have written increase al and increase bx. So that will increase the physical address. Then I write loop again. Okay, and then when I write loop again, the loop command, what it does is it will check whether the cx value is 0 or not. If it is not 0, right, it will go back here. If it is 0, and also while it is going back, it will decrease the value of cl. So I don't have to write a command decrease cl here. Whenever I write loop, the counter is automatically energized. Okay, so cl, so whenever it encounters an instruction of loop, it will decrease the value of cl automatically, and if cl is not 0, it will go back here. So this will run 4 times till cl is 0, and each time the value of al and bl will al and bx will increase. So in consecutive this thing physical address, the values of 0 1 2 3 4 will get. So if I just run at the end of it, let me just okay, I will have these values coming in like this. Okay, is it okay? This is just an example of a small program. How do we
So whenever we are doing whenever we are writing a loop instruction in assembly, only the CX register is used for the looping value, sir.
yeah, correct. Okay, the cl will be continuously decreased automatically. Okay, and the cx will be decreasing every time it encounters. Okay,
So whatever value we put in CL, that many times the loop will execute.
yeah, that it will keep decreasing every time loop. Before executing the loop command, it will check for the value of the cl. Okay, if is it 0, if it is 0, it will exit the loop. If it is not 0, it will decrease the value of cl and go to the position where it is. This is actually in when we write the here, right, in this not an you can't call this an assembly language actually. Okay, this is a language which is which can be interpreted by the compiler. In the assembly language, we need to write if you see the 8086 instructions, loop, and we need to specify the memory address here, whatever it is. Okay, we need to when we write a code here, right, each this is the this particular move might be in some memory location, right, in the code, in the within the code segment. Okay, so that particular memory location needs to be written here, but it will be slightly complicated if we start writing figures everywhere. So most of the compilers, they give us the flexibility of writing these again and again here, and it, but whereas when this is converted into an actual assembly language, then we need to specify the memory location. Here again is representing a memory location where it has to jump and go. Is it okay? No. See, when we use the loop, it will be the CL register. If you want to use a counter kind of thing, right, then we don't use the loop command in that case. Suppose we want to use say register DX as a counter, so we can say move DX here. Instead of CL, I can write move DL04. Okay, and then I can write increase BX and decrease DL. Okay, it will decrease the value, and then jump if not 0 to again. Okay, so I can use that kind of commands also, right? When I write loop, it is with CL or CX, whereas if I have to use a register as a counter, I can do that. I can say I can use DL, AL, whatever register I want. Okay, now I can decrease the value of the DL. Okay, and then I can use the value like jump if not 0. Those kind of commands are also there, so we can use those kind of commands to jump to make a jump statement. Is it okay? Okay, so okay, now let's come back to our problem where we are doing move AX and indirect addressing. Okay, now let's see the opcode remains same 00010. D is the direction, and because now here again it has to be 1 because it is from a memory location to the register, so this has to be registered. There is no option, so D becomes 1. AX W is equal to 1. Now again mod is 00, right, and register A stands for 000, and this is memory corresponding to B, which is 111, right, and BX. So if you see mod 00, so if you see BX, it is 111. So we write 111 here, right? This is with no displacement. It is with no displacement 111 here, right? So this is the. Is it okay? Right? Even in tutorials, I will give you some problems. So once you practice few of them, it will be very clear. Okay. So is this part clear? Anybody has got any doubt where these has come? You just have to refer the output. So why does D have to be 1? Okay, because we have, this is going to be register. This place always has a is register. Here we can give register stroke memory. Okay, so now if you see, since if it is a register to register, okay, then I can place one register here and the second register here, and it can move, because in this case AX, there is one register and one memory, so this becomes fixed. So this has to be AX. Now if this is AX and the data has to be moved into AX, so it has to be from so the direction has to be from right to left. So this is D has to be 1 itself. So there is no option available here. Is it okay, Abhipal? Okay.
Excuse me, sir.
Yeah, tell me.
Sir, here our objective is to move the data stored in the memory location whose value is stored in BX, right? BX stores a value and that's the memory location. We move the data stored in that location,
yeah,
to AX.
BX, if we speak technically, BX contains the offset of the memory location.
Yes, sir, understood.
Correct. BX is not doesn't have the data. It just has the displacement or offset, you can call it, or offset of the memory location, right? Whereas the code, the data segment contains the MSB of the. So using BX and DS, the memory location will be computed. Correct. Okay. Now let us take one more example. Move BX plus SI, right? So what it does is, so this is an example given. Let me just if bx is this, if si is this, and ds is this, the physical address which will be calculated will be like this. Okay, ds into 10 plus whatever is there in bx plus whatever is there in si. So this will be the physical address, actual physical address. And in these physical address, if this is the data 74 and 82 which is already stored, when we move the data, so this is the MSB, so 82 will come here and 74 will come here into AX. So this is the data which is, so this is the lesser significant bits, and this is the higher significant bits. Okay, so this is how the finally it would happen. So if you try to write an opcode for that, okay, this remains same, right? Now if you have to see direction again, because there is a register here, is a memory here, so this gets fixed. Okay, so the direction gets fixed as 1. W mod is going to be 0 0 because there is no displacement here. Okay, displacement is when we give some numerical value. We'll see that example also, right? AX stands for 0 0 0 0, and then from this mod 0 0 table, if you see bx plus si, bx plus si is 0 0 0, so we write 0 0 0 0 here, right? So this is how this is done. Now if you take one more example, where now I am writing bx plus 34, that means there is a displacement here, right? Okay, here. So now if you see the opcode will be the same. Direction again has to be 1 because this is register. So mod word is 1 because it is. Now mod is like, if you see memory mode with 8-bit displacement, this is an 8-bit displacement, right? Now so the mod becomes an 0 1 here, so 0 1 here, so the mod becomes 0 1. Register AX is 0 0 0, and now it is BX plus 34. Now you have to see in 0 1, right? So now what is it? BX plus displacement 8, it is 1 1 1. If you see from this table, so 1 1 1, you write 1 1 1 here, bx plus d8, so this is d8, and then we need to also write the displacement. What is the actual displacement which you require? This 34, so this 34 also will come here. So the opcode will be this much, 8B4734. Okay, is it clear here?
So in the previous example, we used move AX, BX plus SI.
Yeah.
So there SI will be the displacement, and here 34 is the displacement.
SI is not an yeah, that is a, but that BX plus SI that comes under it is not really called as a displacement, it is within a register, so it comes under 0 0. If you see, it is BX plus SI is available here, right? Displacement is when we give some numerical value. Is it okay? That's why the mod is different.
So only displacement is considered only when we give the value manually.
Yeah, when we give the numerical value. When we give the numerical value. Is it okay? Okay. So we take one more example where we are moving SI plus 600, right? So here the difference is this is the memory location, this is the register. Okay, so now obviously this is going to be the register. So now here if you see the D has to be 0 here, because from register you are going to the memory location. Okay, and then mod is going to be see, this is going to be the mod is, it is 600 out here, so it is 16-bit displacement actually, right? It is not 8-bit, so it is going to be, mod is going to be 1 0 here instead of 0 1. Last time it was 8-bit displacement, now it is going to be 1 0 here, right? A register for BH is 111, that we get from this table. BH is 111, right? And then R stroke M, what we need to see is SI plus D16. So 1 0, if you see SI plus D16 here, it is 1 0 0. So I write 1 0 0 here, and then here we need to be careful, right? This is 0600, right? 0600, so we write 06 here and 00 here, right? So this is the lower displacement, this is the higher displacement. Is this clear to all of you? Okay, so yeah, okay, so that's all. I think today we just managed to finish on time. Okay, so to today's class I didn't want to introduce new, so I think now you are all if I put another 4 or 5 problems in a tutorial, you will all be absolutely clear about how to write an opcode from an instruction. So and I'll accordingly frame few questions, and then you can try to find out in the net. If you just search, you will get lot of examples. Okay, so you need to practice this, okay, because there could be some confusion in what is the actual mode mod to be selected, and also before exam I will suggest you all practice few problems from the net and your textbooks also, so that because these all, if you select a these are all where sure shot you can score 100% marks. Okay, these kind of questions, if you are a bit careful and if you do a little bit of practice. So that's all for today. If there are any doubts, then we can handle that. No, Ruben, actually